Hello, in this video I'm going to show you how to create a sphere just like this one using MATLAB 2020 revision B. So let's go to MATLAB. Before we move forward, I want to mention that there's already a function that generates the sphere in just one line, and it's the sphere function. It has one input, or well, more inputs. You have to read this to see which of these fit what you want to do. But what I'm going to be showing you is what basically happens behind that function. So yeah, I'm going to link this on the description. Here I have opened a new live script because it's easier to see the outputs, and we're going to start writing the code for the sphere. The first thing we're going to do is to define the variables that we're going to be using. So a sphere only needs one variable to be fully defined, which is the radius or the diameter. In this case, we're going to give it a value of 1. Then what we're going to do is that we are going to be creating something like this. So here you can see how the Earth is divided into some lines that are vertical and some lines that are horizontal, and the vertical lines all coincide at 2 points, which would be at the North Pole and at the South Pole. These points are called singularities. What we're going to do is the same thing we did for the cylinder. If you haven't seen that video, I'll link it on the description, which is divide the geometry into cross sections. So each cross section is going to be one of these circles right here. So the first singularity, or whatever you're going to start either from the north or the south, that's going to be the first cross section. The next one is going to be this circle right here, then the third cross section, fourth, all the way until we reach the next singularity. The axis of this geometry is going to be along the two singularities. So the x and y coordinates for all the points in the singularity cross-section is going to be 0. Just want to point that out before moving forward. Okay, so having said that, I'm going to set the number of cross-sections that we want, and let's choose, let's say 10 for now. And then the number of points, a number of points per cross-section, or nodes. So let's call them nodes. Okay, so the strategy that we are going to be using for this is to create 3 matrices. One is going to be to store all the x values for each of the coordinates in the sphere, another one for the y coordinates, and another one for the z coordinates. The way we're going to structure these matrices is going to be each row is going to represent one cross-section. So we're going to start from the first row is going to be a first singularity, and it's going to go all the way down until the last row, which is going to be the last or the second singularity. And each column of those rows is going to represent 1 point in that cross section. So in the end, we're going to have 3 matrices, x, y, and z, which are going to be size NCS times n nodes. So in our case, 10 by 10. So right now, what we're going to do is to, before generating any cross section, I want to first take a look at the profile of the sphere, because the cross sections are not going to have the same radius. Each one of them is going to have a local radius, which is going to depend on the profile of the sphere. And the profile of the sphere, because it's a sphere, is going to be an arc. It's going to be a semicircle. So what we're going to do right now is to construct a semicircle that's going to be of radius 1, and is going to have as number of points the number of cross sections that we want. And we're going to find for each of these points, we're going to have the x and y values. The x value is going to tell us our distance away from the origin, and the y values is going to tell us the local radius of each cross section. So hopefully as I write the code, it's going to be clearer. So first of all, this is the equation to generate a semicircle or a circle, but I haven't gotten it to work good for the purposes of this video. So we're going to be using the parameterization of those equations. We can go ahead and write them. So Rx is equal to, Rx is the x values of these local radiuses. So just copy this, paste it here. Then we do the same thing for the y points. And all we have to do is define the angle. So here I could define the angle theta as going from 0 to pi, and the spacing is going to be, in this case I don't want to use the lean space function, so I'm going to define the spacing between each point, which I want it to be pi divided by the number of cross sections. Okay, so I could create a new variable for this, but it's not necessary. I can just copy this whole thing and replace it here and here. We generate this, and we're going to get our x and y values. Remember that these are in Cartesian coordinates, so we can plot them using plot. We're going to plot our x and our y. And we're also going to do axis equal. Okay, so you can see how we've created a arc. So what we're interested here is at each of these points, let me just change the type of plot so it's easier to see. Okay, so at each of these points, we're going to get the local radius. And the local radius is going to be equal to the y value here. So for example, the local cross-section is going to, at cross-section number 2, the local radius at cross-section number 2 is going to be equal to 0.3 in that case. Our x is going to be the distance away from the origin. So the origin in our case is going to be at 0. This point is going to be, this cross-section is going to be a distance -1 away from the origins. The next step is to create each of these cross-sections, and we can do them right away because we already have the local radius for each cross-sections, and since all of them are circles, all the points in those cross-sections are going to have the same radius, the same local radius. All we have to do is create a value for the angular position of those nodes, right? And what we're going to do is going to go from 0. In this case, we're going to do 2 pi divided by the number of nodes, and it's going to go to 2 pi. Okay, so we have created the vector containing the angular values for one cross-section, but all the cross-sections are going to have the same angular values for their nodes, because all we're doing is scaling them up or down depending on the local radius. Okay, so instead of repeating the number of rows to create a matrix with all the cross-sections, what I want to do is to use another function, which is the meshgrid function, which is what's going to do is going to do the same, but it's a little bit faster. So I'm going to leave the documentation for this function in the description of this video in case you don't know how to use it. So the outputs are going to be theta, let's just keep the same, in our y, which is the local radiuses. And the inputs are going to be theta, the vector theta, in same ry. So when we run this, we're going to get, now we're going to get 2 arrays. You can see that now is 11 by 11 and 11 by 11. Is 11 because since we're not using linspace, we're using this way of creating the vectors, is always going to be 1 plus the number we define here, so it's 11. Here you can see that the first cross-section is all the nodes are going to have a radius of 0, which is what we want because it's a singularity, and so is the last cross-section. These are really small numbers, consider it 0. Then it grows all the way to 1, which is the maximum radius of our cross-section. And then for the theta values, you can see that they are all the same. Each cross-section is going to have the same thing. All we are doing is just scaling up and down the circular cross-sections. What we are going to do next is to convert these equations to Cartesian coordinates using the pull-to-cart function. So we're going to get matrix X and matrix Y. Pull-to-cart, and the inputs are going to be theta and ry. And let's run a test to see if everything up to now is fine. So I'm going to plot each of the cross sections one by one, and we should get a bunch of circles of different sizes. So the way I'm going to do this is for I that goes from 1 to the number of sections, plot X I row that, and also we can do the same thing for Y. We do the same thing for Y, and we tell the program to hold on, run it. There you go. Well, it's not a real, it's not really a circle. Let's just increase the to 100 points for now. So yeah, you can see. So each of these is a cross section. You cannot see. There's a little point here. There should be one. That's the first cross section. It's going to grow to the next one, the next one, the next one, the next one, until it reaches the maximum radius cross section, which is a radius of 1, and then starts to decrease until the singularity again. Okay, so all we have to do now is to define the C vector. Remember that the C vector is going to tell us where these cross sections are positioned along the axis of the sphere. And remember that the axis of the sphere is aligned with the singularities of the sphere. In this case, it's going to be here in the center of the circles, and it's going to come out of the screen and into the screen. We have already calculated that those values, and these are Rx value. Here you can see them. That goes from 1 to -1. Remember that the two extremes have to be equal to the radius, and if a radius is 1, then two extremes have to be equal to the radius, or at least the position of them. So C is going to be equal to, I'm going to flip LR. I'm going to flip this function first, and then I'm going to transpose it. Why flipping it? Because I want to start from the negative point and work all the way up to the highest point. And then I'm going to transpose it because remember that all the matrices are defined by cross sections, and all the points in, let's say, in the first cross sections are going to be a distance 1 away from the origin, -1 away from the origin. So we have to repeat this number for all the nodes in the cross section, and then we're going to repeat this number for the second cross section, third number, all the way until we reach the last cross section. And we're going to do that using the repmat function. I'm going to repeat the vector C, 1 row, and then the number of points, nodes, +1. Remember, I told you that whatever value you put here, you have to add +1 because of this way of writing the vector. If we were using linspace, you wouldn't need to write a +1 here. Okay, let's just check that the matrix all the matrices have the same size. Yeah, 11 by 101. We have 11 cross sections and 101 points per cross section. And all we have to do is to plot it. X, Y, and Z. See? There you go. That's it. There's the sphere. It doesn't look like a sphere. And yeah, there you go. So it looks more like a sphere. You can see that it's kind of coarse. The curvature of the sphere, that can be improved if you increase the number of cross sections. There you go. Oops, sorry. There you go. You can see the two singularities up here and up here. If you want the singularities to be along the horizontal line, all you have to do is swap X with Z, and there you go. So in case you want to export this geometry for 3D printing, FEA, CFD, etc., you can go to MathWorks and download this function right here. This function is going to create whatever you're plotting with the surf function. It's going to convert an STL file out of it. And the way that you do that is that you save that function in the same directory as your working directory here in your file. And what you do is you call it first, surf2stl is equal to, sorry, not equal to, open parentheses. The first argument is going to be the name. So sphere.stl, you have to add the extension, and the next 3 arguments are going to be the coordinates. Tells you how many faces the geometry has. That's quite a lot of faces, but it's a sphere, so you want it to have a really smooth curvature. There you go. Well, I hope you found this video helpful. If you have any questions, leave it on the comments of this video. I'll try to answer them as best as I can.